I got it.
Although, you know what?
You'll like heat transfer. Pretty good shit.
All right, see you tomorrow, man.
Let's see.
Yeah, I gotta turn it. Is there supposed to be a conjugation page on there?
You don't believe me, then?
Well, I don't know.
There is. No, I'm telling
Caesar
you.
didn't have one.
No,
Nah.
it literally said on the document thing.
So I'm gonna put a contribution, but like who did the slides or?
Yeah, let's see that. That's what I'm saying. I don't know.
No, I saw that yesterday.
Yeah.
I just assumed, well, I mean. I didn't know if it was for the PSU. I thought it was just.
For like anything.
Well, yeah, just like what we did. But I mean, even then, it's kind of like. It was like a team effort.
Yeah, I don't know, to be honest. I don't even know.
It was more like it was that simple. I don't know why there has to be 3 modules.
Yeah.
I'm just gonna say 3D print, fucking neck, and then order materials, so and you and me. I don't know.
Machine shop.
Yeah, something like that. Something like that. If that's what he means, and then slides 1 through whatever is gonna be team. Like,
Yeah.
decision.
I think he's making it like much more complex than how you made it sound.
Yeah, but I think it's for. Did you look it over? Yeah, it's fine. I think that was for another team.
Oh, I see.
You stay in this class?
Yeah. Still.
Okay.
All right, man. See you. I'll see you tomorrow.
Really shop.
I feel like I'm going to time for that place, but yeah. I feel like it is gonna be more lively. Dr. Shaw.
Yep. What's up?
Good question. For the homework, did you just want, I guess, like first problem and then just the entire script for the rest?
Sure. Yeah, that works. Yep.
Like we don't need to show our result, right, of the MATLAB?
No,
Just the- okay.
Yeah. I mean, for the homework for this class, I'm grading it mostly on completion anyway. And so the MATLAB problems are just there for you guys to practice. So
Well, I did have a question on 3C.
Yeah.
If we got the same answer, but the code was a little different, is that okay?
So I mean, these are all, all MATLAB codes that are going to be useful like later on in some way. And so, I chose the structure of those loops, just, for that purpose. And so, I mean, at the end of the day, is if you got the same result and you gave it a good effort, you'll get credit for it. But then it would be good to, maybe after the homeworks to check the solutions just to make sure that, you can kind of follow my logic for that.
I mean, someone already showed it to me.
Yeah.
But I wanted to keep it. That's what I did.
Yeah, that's cool. All right, it's 5:30, so let's go ahead and get started. Good evening, everyone. And for those of you here in the classroom, welcome back to campus. We're back in campus. Although, if you had me last semester, I actually spent a lot of time in this classroom lecturing from here. So, this is nothing new to me. But if this is your first time back to campus, welcome back. And, let's hope that it's a good semester. All right. And so, I want to apologize a little bit today. I might be a little bit frazzled because the return to campus has been a little bit rocky for me. Actually, last couple of times I saw you guys. Last Wednesday I was really frazzled too, but that was for a different reason. But so I might be a little bit out of it today. And so I would thank you guys for your patience. But I'm going to do the best I can to get through today. Okay. So the plan for today is we're going to start our next set of lecture notes, which is finite differences applied to diffusion equations. And so I think this will be a nice follow-up to what we talked about last Wednesday, because you'll actually see, how we can use all that really abstract math stuff to solve some math equations. And so, but you actually get to see some stuff in action. And, if we move fast enough today, we'll actually get to write some code as well. I know that there's some questions on the homework, and so I do want to go over that as well, just very briefly. We don't have that much time, but I did want to talk about some of the problems, just a little bit of the logic that I had, going into a lot of those loops. Okay. And so I think that's all my announcements. And so, if you have questions on the homework, I would ask that you wait, because I am going to go over the programming questions. But besides that, are there any other questions I can answer before we get started? Okay. All right. So let me go ahead and stop sharing this. Let me go ahead and share my screen. Okay. Put the keyboard up here, of course. Okay. So let me go to the homework. 17. Okay. And so I was talking with someone before the lecture today. Remember the homeworks for this class, they are graded on completion. And so, I'm not going to check, I'm not going to go with the fine tooth comb through your homeworks, but I gave you these coding problems, with some purpose, because a lot of the patterns and a lot of the syntaxes that I gave you here, it's going to show up a lot throughout the class, and so it would be good to kind of not only get the answer for these, get the outputs, but also kind of understand why we did things a certain way, because that's going to help us later on in the class. And so one in particular I've gotten a lot of questions about is this one right here, which is 3C, right? So I did want to talk about this one. And this one actually we'll actually see today if we're fast enough, but if not, probably on Wednesday. Okay, and so you can see here we have a matrix, and so we have a matrix of zeros, 5 by 5, right? And then eventually, we're going to fill the matrix up like this, okay? And so, I think whenever you see a matrix like this, I think what people generally tend to intuitively want to do is they want to do a nested for loop, right? And so that's what you have here in 3B, where the nested for loop visits every single entry in the matrix. But you can see here in the pseudocode, I've only given you one for loop, right? And so that's a little bit strange. And so, how can we build a matrix if we're only having one for loop? Right? And so the logic behind this is that this for loop right here is actually going to loop to visit all the rows, okay? And so, if I can't reveal this here because I don't have the original document, but it would look something like this, and this mouth is super jank. And so it'd be a for loop that goes from 1 to 5, right? Where each iteration of the for loop, we're going to visit a different row, right? And so the first iteration of the loop, we're going to visit the first row. Second iteration, we're going to visit the second row, then the third row, then the fourth row, then the fifth row, okay? And so, we're going to visit all the rows. And the reason I'm doing this row by row is that you'll see that, in the class today, we're going to be building linear systems kind of equation by equation, right? And so if you have a system of linear equations and you use a matrix to represent them, each row represents a different equation, right? And so that's kind of what this is kind of meant to represent is, we're building up a linear system equation by equation. Okay. All right. And so with that out of the way, I want to show you kind of what I like to think of 3 different cases for this matrix. Okay. I'm going to highlight them with different colors. Okay. Okay. And so you can see I've highlighted the first row in blue, right? And so the reason for that is you can see we have a -2 on the diagonal and a 1 to the right of the diagonal, okay? But nothing to the left because there's really nothing to the left of that. For everything in red, you can see I have 2 wingmen, right? So we have a -2 on the diagonal as well as a 1 and a 1 on the left and the right. And then for the purple line, we have a -2 on the diagonal and then a 1 on the left, okay? And so these are the 3 different use cases that you can think of in your if statement, right? Because remember, when you have an if statement inside a for loop, the way that or the reason that we have an if statement in a for loop is that we want the program to do something different on certain iterations of the for loop, right? And so in this case, when we're looping over the rows, we're going to start with the first one, right? And so we're going to visit this one first. And so if we want the loop to do something different on the first row compared to the other ones, then we can input that into the if statement, right? And so this if right here, you can say if row equal 1, right? And so if we're in the first row, then do something, right? Next, we can check to see, maybe we're in the last row. So this else if here would be like the last row, okay? Right? This mouse is jank as fuck. Okay, or else, this would be kind of everything else, right? And so, if we're in the first row, do something. If we're in the last row, do something else. But if we're anywhere else, then do kind of the base case. Okay. And you can see here that from what I've kind of shown you in the matrix, if we're in the first row, we're going to add a 1 to the right. Okay. If we're in the last row, we're going to add a 1 to the left. But if we're in the middle rows, we're going to add a 1 on the left and the right. Okay. So that's what kind of these rows kind of represent. Okay. Right, so the last thing I want to show you, before we come back to the lecture is this last row, right? This last line of code right here, right? So notice how this line of code here is outside the if statement, right? And so this line of code here is going to execute on every single iteration of the loop, right? And so this line of code is never going to be skipped. And so, look at this matrix, right? And look at it row by row, and think of, what is something that happens on every single row of this matrix, right? And so first row, second row, third row, fourth row, fifth row, try to see what's something that happens and where is that location on the row, okay? And remember, this entire time you're looping over the rows. And so, if you say I is equal 1, 2, 5, right? Then your I, for a certain, for a certain iteration of the loop, this is going to be your current row, okay? Okay. Right. And so think about what's happening on every single row, okay? And then use the I in order to guide you into the right locations on that row, okay? All right, so that's all I want to say on this one, because I've already kind of given you a lot of the logic, but I want you guys to kind of write the code from there. Okay. All right, any questions? Any questions on this? Okay. All right, so hopefully that helps you out. I would say this is probably out of all, I mean, they're all important, but this is probably the one that's going to be most immediately applicable, because we're going to see this matrix structure when we're doing our 1D diffusion problems. Okay. The other ones are important too, but make sure you really kind of understand this one. Okay, so let's go ahead and come back to the code or to the notes. I'm borrowing Dr. Lee's iPad because I lost my stylus. That was one of the things that happened today. And so it's going to say Jin Woo's notebook. I didn't change my name. That's just I'm borrowing his iPad. Okay. All right, so the topic for today, I believe this is lecture notes 03 or 04. Okay, so we're going to be learning how to solve 1D diffusion equations with finite differences. Okay. All right, so let's start with their general conservation equation again. Okay, so I'm going to write out the full equation. And so remember, our general conservation equation consists of our unsteady term. So we have partial phi, partial t, plus our convection term. Okay, there's two of them. Then we have our diffusion terms. Okay, then we have our source. Okay. So let me go ahead and label these. So this right here is unsteady. These are the convection terms. These are the diffusion terms, and this right here is the source. Okay. Source term. All right. And so we're not quite ready yet to solve this entire equation. We're going to be spending kind of the first half of the semester building this up. And so kind of my approach to doing this is, let's solve this kind of piece by piece. Okay. And so we're starting with kind of the simplest one that we can do, and that's 1D diffusion. Okay. And so the terms that we're going to focus on are going to be, something from the diffusion terms. Okay. And in fact, we're only going to look at one of them. And so we're just going to look at this term right here. Okay. And just because it doesn't really fit into any other category, we're going to look at this term as well, okay? And so the 1D diffusion equation, after you kind of simplify this, okay. Right? And so everything on the left-hand side is going to be equal to 0, okay? Then we're going to have gamma d squared phi dx squared. I'm changing the derivatives here to normal derivatives because we only have one variable now. So we've gotten rid of t, and we've gotten rid of y, plus q. Okay. And sometimes for simplicity, we often move the q just to the other side of the equation. And since the q is arbitrary at this point, I just kind of flip the sign just to make it a bit more convenient. And so the form of the equation that we're actually going to use is something like this. We have gamma d squared phi dx squared is equal to q. Okay. And so this is the equation that we're going to focus on solving for today. Okay. All right, question. So for 1D diffusion, it's not partial anymore. That's right. Yes. And so you only have partial derivatives when you have more than one independent variable. And so the independent variable are the ones that kind of appear in the bottom of the derivative. And so things like time, things like x, things like y, right? X, y. And so for 1D steady, well, I should say 1D steady diffusion, we're not considering time. And since it's 1D, we're not considering y anymore. And so since x is the only variable that we're going to look at, then we can change the partial derivatives to regular derivatives. Yeah. All right. And what's nice when we do that, and so when we can get rid of the partials, we no longer have a PDE, right? And so what we have right here is an ordinary differential equation. Which is really nice because we actually do know how to solve ordinary differential equations, and so this will be kind of a really nice first step for us. Because the thing that's usually difficult when you're writing code for the first time is you want to know whether your code is working or not, and sometimes that can be really, really hard. But if we're working on kind of more simple problems like this, where we can solve it by hand, we can directly check our computational solution against our hand calculation solution, right? And since they're solving the same problem, we should get the same thing, right? And so this is a great first step for us because it allows us to kind of this will be kind of our first time writing code, and we'll have something that we know we can check our answer against. Okay, and so that's kind of the reason why I chose this one to begin with, because it's because we have that ability for us. Okay, any questions on this? Yeah. Yeah, yeah. So the question is, should there be a negative on the Q? Yeah. So if you're, in normal cases, when we move the Q over to that side, we put a negative on it. But since we're just kind of going on simplicity right now, and Q is kind of undefined at this point, I just kind of absorb that negative into Q, just so we don't have to worry about a negative floating around. But yeah, normally you would have to keep that negative. And later on, once we bring convection and other stuff in, then it's important. It'll be important to keep that sign. Yeah, good question. Okay. All right. So actually, let's start with the analytical solution. And so this will be a little bit of a refresher of 308. Okay. Although not really. This is kind of like baby 308, but I think it's good to review anyway. And so let's look at exact solutions. To 1D diffusion. To 1D diffusion. Okay. Right. And so the nice thing about this is that we have just a second order derivative here, and so we can find the solution just by integrating, right? And so we'll do an example that shows that. But one point I want to make before we get into that is about boundary conditions, right? Whenever you solve a differential equation like this, you always end up with what's called like arbitrary constants, right? And so in order to solve for those constants, you have to apply boundary conditions to solve for them, okay? And the number of boundary conditions that you need for an ordinary differential equation equals the order of the derivative, okay? So for ODEs, boundary conditions okay? And the number of boundary conditions equals order of derivative, highest order. Okay. And so since we have a second order equation here, right? So the order of the derivative is 2. That means we're going to need 2 boundary conditions. Okay. Okay. So there's lots of different ways that we can apply our boundary conditions, or where we can apply them. But kind of the most traditional or the most typical you'll see is that you have boundary conditions at each end of your domain. Okay. Okay. And so what do I mean by that? And so, since we have a 1D equation here, we're going to have a 1D domain, right? And so we're going to be solving our equation on a line that looks like this. Okay. And so just like any other line, we have one end of the line and we have the other end of the line, right? But just for simplicity, I'll draw the lines horizontally. And so there'll be a left-hand side and a right-hand side. Okay. And so when I say that the boundary conditions are given at the ends, that means one of the boundary conditions is going to define our solution behavior here, and the other is going to define our solution behavior there. Okay. Okay. And so we're going to have one boundary condition each on each side. Okay. So strictly speaking, this is not a hard requirement, because mathematically you can solve a differential equation by having multiple boundary conditions on one location, right? And so another way that you can solve this is to say, give me two boundary conditions here on the left-hand side. And mathematically, that's actually just fine. So you can solve for an equation like that. But for physical problems, which are the ones that we're going to be solving for, like heat transfer, it's most traditional to have, one boundary condition on the left and one boundary condition on the right. Okay. All right. Any questions on this so far? Yeah.
Does that mean there's two on the left and two on the right, or is the two split up?
The two is split up. And so we have one on the left, one on the right. Yeah. Mm-hmm. Yeah, and this is going to extrapolate to 2D as well. So when we have 2D, we're going to have a two-dimensional domain, and then we're going to have just one boundary condition per edge. Yeah. Okay. All right. So let's talk about the types of boundary conditions that we can apply, because that's also kind of important. Okay. And so there's two types of boundary conditions that we have, and the way that we differentiate them is by how they're mathematically applied. Okay. Okay. And so the first type of boundary condition that we have is called a Dirichlet boundary condition. Okay. Probably named after some dude, but honestly, I've never cared enough to look him up. Okay. And so a Dirichlet boundary condition, the way that this is applied is it's when we make a direct application or direct specification of the solution at the boundary. Okay. Right, so what does that look like? And so, remember our solution variable is phi, right? And so when we say phi at x is equal to xb, right? Where xb is I'm denoting that's going to be the location of the boundary. Okay. This is going to equal to some specified value phi naught. Okay. So that's a Dirichlet boundary condition. Okay? So when we know what the solution variable is going to be, or solution value, and we directly specify that in the equation, that's Dirichlet. Okay, so the other type of boundary condition that we have is known as a Neumann type boundary condition. Again, probably named after some dude, but never cared enough to look him up. And so a Neumann boundary condition, it actually has a very broad definition, and so it can mean a lot of different things. But for the purpose of this class, I'm going to give you kind of a simple definition of it. And so a Neumann boundary condition is when we apply a condition on the solution derivative. Okay? And so what does that look like, right? And so it looks something like this. And so if we, again, our solution variable is phi, okay? Right, and so if we say that d phi dx at x is equal to xb, this is equal to some value gamma, okay? Where gamma here is going to be given to you. This is what's known as a Neumann type boundary condition, okay? And so in the next example, I'll show you how both of these are assigned kind of mathematically. But I wanted to make the distinction between them, before we hop into an example. Okay. All right, any questions on this before we do an example? Okay. All right, so let's put this all together into an example. Maybe this is a review of 308. So hopefully we can go this kind of fast. Okay. All right, and so let's consider the 1D diffusion equation with a constant source term. Okay. And so we have d squared phi dx squared, okay, is equal to 6x. Okay. And so there's our equation. And then we have the following boundary conditions to help us solve it. All right, so the first boundary condition is going to be at x is equal to 0. And so when x is equal to 0, we're going to say the solution value is directly going to be 1. Okay. And then our other boundary condition is going to be at x is equal to 1. Okay. Okay. And we're going to say that the derivative of the solution at x is equal to 1 is going to be 0. Okay. And so right away, what you can see, based on where the boundary conditions are, you can see we have one boundary at x is equal to 0, and the other boundary is at x is equal to 1. And so if you draw the domain, okay, we have a one-dimensional domain because we're solving a 1D diffusion equation. On one side, we have x is equal to 0. The other side, we have x is equal to 1. Okay. And the boundary conditions here are going to be phi of 0 is going to be 1. And on the other hand, we have other side, we have d phi dx at x is equal to 1 is equal to 0. Right? So this is kind of a visual representation of our boundary conditions. All right. Any questions on the problem setup before we go about solving it? Okay. All right. And so since this is just a simple diffusion equation, we have two derivatives here. Well, actually, let me write out. Solve for full solution. Bless you. So we're basically solving for phi of x. Okay. All right. And so the way that we can solve this, because we just have a simple derivative here, no extra terms, we can just do that simply by integrating, okay? All right, and so we have d squared phi dx squared is equal to 6x, right? So let's go ahead and perform one integral here. Okay, and we're going to perform the integral with respect to x. And so on one side of the equation, we integrate a second order derivative. And so we do that takes off one of the derivatives. So we have d phi dx on one side. Okay. On the other side, we're going to integrate 6x. The integral of 6x is 3x squared. Okay. And since we're doing an indefinite integral here, we have to add an arbitrary constant. And so our arbitrary constant here is going to be C1. Right? Right. But we're not done yet. We need another one. Right? And so we're going to integrate one more time. And so if we integrate one more time, the derivatives on the left-hand side are going to go away. And so we're just left with phi of x. On the right-hand side, we're going to integrate 3x squared, which is just x cubed. Okay. Then we're going to integrate C1, which is just a constant. And so integral of C1 is going to be C1x. And then finally, we have C2, which is our, our last arbitrary constant. And so this equation right here, this is our general solution. And so now what we need to do is we need to apply boundary conditions and solve for C1, C2. Okay. All right, any questions on how we got that on that general solution? Okay. All right, so let's go ahead and start applying boundary conditions. All right, so let's start with the condition at x is equal to 0. And so this is not in the textbooks. This is just kind of me giving you guys good advice, right? And so usually for these 1D problems, x is equal to 0 is going to be part of your domain. And that's usually a good place to start. And so that's usually a good place to apply your first boundary condition, just because a lot of things will usually cancel in the equation because of that. Because if you started with the other side, like you can do it, but then a lot of times you'll end up with multiple unknowns in that equation. Right? And so if you start with x equal to 0, you can usually solve for one of the constants outright. Right? Usually, not always, but usually. Okay, so let's go ahead and do that. And so our boundary condition at x is equal to 0, remember, was a Dirichlet boundary condition, right? Because we're directly specifying our solution value there. Okay? And so we have x of 0. And so if we plug in 0 into this equation, we have 0 cubed plus C1 times 0 plus C2, right? And so I just plugged in 0 into our general equation. And then according to our boundary condition, you can see here that our solution there is going to be 1, right? And so our full equation is x phi of 0 is equal to 0 cubed plus C1 0 plus C2 is equal to 1. Right? Of course, we're going to cancel out those terms because they, they're just multiplied by 0. And then what we're left with is C2 is equal to 1. Okay? And so just like I promised you in this, before we started this, if you apply the boundary condition to x equals 0, you can solve for one of them outright. Right? And so right away after we apply this boundary condition, we found that C2 is equal to 1. Okay. All right, so now let's look at the other boundary condition. And so the other boundary condition says that d phi dx at x is equal to 1. Okay. This is equal to 0. Right, so let's go ahead and take the derivative of this. And so we have 3x squared plus c1, right? And so I just took the derivative of our general solution. Okay? And then let's apply this at x is equal to 1. Okay. And so if we do that, we get 3 times 1 squared plus c1 equal to 0. Okay. And then from here, we can just solve for c1. Right. And so we solve for c1, we get c1 is equal to minus 3. All right, so let's go ahead and plug this back into the general equation, okay? And so after we plug this back in, we get phi of x is equal to x cubed minus 3x plus 1. Okay. And this right here is our full solution. Right, any questions on how we apply the boundary conditions here? Okay, all right. And so just because it'll help us later when we're looking at the solution, I'm gonna go ahead and plot this for you. Okay. And so the plot of the solution looks something like this. So we have x, and this is phi of x. Okay. And so we're going to start up here. And so remember x, phi of 0 is equal to 1. Okay. And then if you plot this function, it looks something like this. For this right here, this would be x is equal to 1. And so we have kind of like a declining kind of slide looking thing. Okay, so burn this graph into your memory because once we solve this equation computationally, we're going to see if we get the exact same graph. Okay, because if we can get the same graph, that means our computational method is working. Okay, because all we've done so far is we've kind of just done a review of 308 or wherever you learn differential equations, and we got the exact solution to this problem. Right, and so now we want to see if we can get the same answer using computational methods. All right, and so to that end, the next section that we're going to go over is the actual finite difference solution to 1D diffusion. All right. Okay. And so, let's recall what we talked about last Wednesday, right? And so last Wednesday, we learned this technique called finite differences. And the whole idea with finite differences is to take a differential equation or take a derivative, at its base case, and then turn it into an algebraic expression, okay? Okay. Because the example that we just did, we basically solved the differential equation directly, right? And so we said we have this differential equation. Let's apply some calculus, which in this case was just kind of some simple integrals and some boundary conditions, and let's use that to find the solution. Okay. Finite differences takes a very different approach, and so finite differences it'll start with the same differential equation, but instead of solving the differential equation exactly, what we're going to do first is we're going to transform it into a system of linear equations. Okay, and so our goal with this section is to say, how can we take a differential equation and transform it into a system of linear equations, okay? And so remember, a system of linear equations is basically, algebraic equations that says, we have 5 unknowns, so let's come up with 5 algebraic equations to solve for this, okay? Okay, so visually, it might look something like this. And so if we just, take the previous example, right? And so we're going to apply finite differences. Okay. And so instead, we're going to have something that looks like this. So we're going to have a matrix set of equations. Okay. And so we're going to have, something that looks like that. Okay. And remember, both sides of this, I know when you're first looking at this, both sides of this equation look awful. And so it's like transforming from one bad thing to another one. But remember, the key to this is that computers are really good at this, right? Right. And so if we can use some manipulations, if we can use some theory in order to get this, then the computer can just kind of take it from there and solve it really quickly. Okay, and so in order to actually get to that point, there's actually quite a few steps involved. Okay, and so the first step that we're going to do is we need to discretize our domain. Okay. Okay. And so what do I mean by discretize? And so when you discretize your domain, you basically take your your computational domain and break it up into discrete parts. Okay. Right. And so for 1D, I admit it seems kind of silly to do it because in 1D we only have line domains. Okay. And so when I say we want to discretize our domain, we're going to go from a continuous line here, where we have our 2 endpoints, and then we have our our 2 endpoints like that. And when we discretize, right? And so what's a smaller version of a line? It's just a smaller line, right? And so we're going to take our big line and break it up into a bunch of smaller lines. Okay. Right. And what you can say is that they're like a bunch of small line segments. But one thing I'm going to do, because we're going through the trouble of discretizing our domain, I'm going to go ahead and label all of the nodes. Okay. Right. So each point, each grid point that we're discretizing with, I'm going to call that a node. And another thing I'm going to define on this domain is I'm going to define the spacing in between the nodes. Okay. Okay, so delta x here is what's known as the grid spacing. And its definition is basically just the physical distance in between each of the nodes. Okay. So that's gonna be important important later. All right. Okay. And so now that we've discretized our domain, right? And so we have kind of this grid version of our domain. Our next step is to discretize our equation. Okay. And so this is where we're actually going to apply finite differences. All right. And so I'm actually going to use a generic form for this, just so you can apply this to all 1D finite differences. Okay. And so our generic 1D finite generic 1D diffusion equation is gamma d squared phi dx squared is equal to q. Okay. And so if we apply finite differences, right, we're going to take that derivative and then we're going to replace it with a finite difference representation. Okay. All right. So we're going to have gamma, and so the gamma is still going to stay there. Okay. But instead of that second order derivative, remember we went over our, and for second derivatives, it's just the central difference scheme. Okay. And so for that, we have phi I minus 1 minus 2 phi I plus phi I plus 1. Okay. All divided by delta x squared. Okay. And so that's the replacement that we're going to make. And this is going to be equal to qi. Okay. And so this right here, this is our finite difference representation of our, of our 1D diffusion equation. Okay. Okay. Any questions on any of this so far? So I've just kind of been going on for a while. Okay. Okay. All right. So how are we going to use this? Okay. And so the way that we're going to use this, equation is that we're basically going to take this equation and then apply it on each node, or apply it on each of the grid points in our domain. Okay. Right. And so if we have 5 different grid points in our domain, we're going to apply this 5 different times. Okay. And so what you can imagine, as we apply this on each of the different nodes in our domain, it's going to grant us an additional equation each time. Okay. Okay. And in particular, the type of equation that we're going to get is an algebraic one. Okay. And so the way that we kind of proceed from here is that now that we have our finite difference scheme, and so in other words, now that we have this equation, the next step is just to kind of methodically apply this to every node in our domain until we have enough equations to solve for the solution at every grid point. Okay. Okay. And so the last part of this of this point here is kind of the most key. Okay. And so, we went through the trouble of taking our domain and discretizing into discrete points. Okay. And so our goal then is for each of the points that we discretize that, we want to find out what the discrete solution value is at that point. Okay. And so let me draw you an image just to kind of make it clear, because I think that description is a little bit vague. Okay. All right, so here's our domain, right? And so our domain starts at x is equal to 0, and let's say it ends at x is equal to 1, right? Right, and so let's say that we discretize our domain into that many points, right? And so if we label the nodes, right? So here, let's say we have 8 nodes, okay? Our solution, our background solution, remember, looks something like this, right? And so we start at 1, and it's going to go down like that, right? Approximately. And so when we solve for a finite difference solution, we don't get the smooth curve. What we get instead are kind of discrete points along this curve. Okay. Okay. And so kind of imagine that the curve behind it is gone. And so let me go ahead and kind of get rid of that. Okay. Wow, I love this like that. I might steal this from Dr. Lee. And so what we're going to get from finite differences is something like this, right? And so we're going to get a discrete list. Okay. Where instead of kind of that continuous curve, we're going to get the solution at these discrete points. Okay. And so, for the 8 grid points, we're going to get 8 solution values. Okay. And then to obtain these solutions, we would have needed to solve, 8 algebraic equations. Okay, and again, the way that we get those algebraic equations is through an application of the application of our finite difference approximation. Okay. All right, and so all that sounds really nice and magical, but it all still sounds very abstract. And so the next thing I'm going to do is I'm actually going to apply this to our example problem, just so that you can kind of see it step by step, throughout the whole process. And hopefully kind of everything kind of becomes a bit more clear from that. Okay.
Quick question.
Yeah.
So if we say, going back to your boundary conditions from kind of like the edges.
Yeah.
How would this work? So we would still need 8 boundary conditions, but just that at point 0 and 8, we have specific boundary conditions?
Right. Yes.
And, okay.
Yeah. So that's a good question. So, boundary conditions does make this a bit complicated. Because those are going to change our equations. And so you'll see that, when we try to apply our finite difference to this node and this node, we actually won't be able to do it because we don't have any neighbors to the left or to the right on in the case of node 8. And so for those ones, you have to use special equations based on the boundary conditions. Yeah, that's a good point. Yeah, we'll get that. Question back there too?
I was gonna add on to this point, like, what if we take a sum like the Riemann sum? That compose it.
Yeah, no, this is it looks very similar to the Riemann sum. So what you get from the solution, because The Riemann sum, you basically, you approximate the solution values at those locations, and you take kind of the area around that. And so visually, it looks very similar to that. Yeah, but we're kind of doing the. Well, it's pretty similar. It's just the way that we approach it's going to be different. Yeah. Mhm. Okay. All right. So let's go ahead and run through a whole example of this, just so you can kind of see from start to finish. Okay. All right. And so in this example, let's say that we have our same equation from before. Okay. Okay. All right, so we have d squared phi dx squared is equal to 6x, okay? And then our boundary conditions. Okay. Our boundary conditions, we have phi at x equal to 0 is equal to 1. And our other boundary conditions at d phi dx at x is equal to 1 is equal to 0, okay? But instead of solving this equation exactly, let's solve for a finite difference solution on a grid of 5 points. Okay. 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 And so there's our domain, right? And so we've, the problems kind of discretize your domain for you. And so, you can see here that we have these 5 points, and we want to solve for the finite difference solution, on these 5 points. And so we're going to apply basically our finite difference formula to this, okay? And then use that to solve for the solution. Okay. All right. So first step, let's, now that we've already discretized our domain, let's take our equation and discretize it, okay? All right, and so just like we did, just like we did up there, we have our derivative term here. And so let's replace that with its finite difference approximation, right? So we have phi I minus 1 minus 2 phi I plus phi I plus 1 divided by delta x squared, okay? Right. And then on the right-hand side, just to make things a little bit simpler, whenever you see x, I'm going to replace it with x sub I, right? And I'll show you what that means, later on when we're actually plugging in numbers. Okay? Right. And so let's go ahead and simplify this. I'm going to go ahead and multiply by delta x on both sides, or delta x squared, excuse me. Okay. Well, remember, delta x is the grid spacing, right? So delta x is going to be the distance in between each of the grid points here, right? And so if we assume that the grid is evenly spaced, where this is x equal to 0, x equal to 1, right? And you can see here we have 4 spaces and 5 nodes, right? We can see here that delta x is just going to be simply 1 divided by our 4 spaces, right? And so, our delta x here is going to be 1 over 4 or 0.25. And so if we apply that to our equation here, on the left-hand side, we have phi I minus 1 minus 2 phi I plus phi I plus 1, okay, is equal to 6 divided by 4 squared, which is 16, okay, xi. And so we can go ahead and simplify this fraction. And so it's going to be equal to 3/8 xi. Okay. Okay. Now that we have our finite difference equation here, we can apply this on every node in our domain.
Sorry, one more time.
Yeah.
Do you mind showing delta x? How to calculate that?
Sure. So the delta x is the spacing in between each of the grid points. And so here we have 5 different grid points. And so the number of spaces that we have is always going to be n minus 1. And so we have 5 grid points. We have 5 spaces. We have space 1, space 2, space 3, space 4, right? And so since our domain goes from 0 to 1, then the length of the domain, or L, is 1, right? And so we take the length of our domain, divide by the number of spaces, which is 4. And so that gives us 0.25, or 1/4.
Thank you.
Yep. Mhm. All right, question. So how did I get 616? And so the way I got 616 was I had I multiplied both sides by delta x squared. And so remember delta x is 1/4. And so this is multiplied by 1/4 squared, right? And so 1/4 squared is 1/16. Yeah. And so I did 6/16 simplified to 3/8. Okay. And so let's go ahead and apply this to each node in our grid. Okay. And so that's going to give us 5 equations. Okay, so I'm going to list out the 5 equations, 1, 2, 3, 4, 5. Okay. And so actually, let me do this. All right. And so for each of these equations, the way that we're going to apply them is I'm going to set I equal to that node number. Okay. And so when I say I'm making the equation for node 1, that means I'm going to set I is equal to 1. Yes, and so right before the 3/8, that is an equal. So all I did here is I just simplified the fraction from 6/16 to 3/8. Yeah. Okay. All right, and so if we set I is equal to 1 in this equation, we have phi I minus 1, and so that's going to be phi 0 minus 2 phi I, and so this is going to be 2 phi 1 plus phi I plus 1, which is 2. Okay. And that's going to be equal to 3/8 times x1. Right, and then we have the exact same thing for the second node, right? And so we plug in I is equal to 2. We have phi I minus 1, and so that's going to be phi 1 minus 2 phi 2 plus phi 3, and that's going to be equal to 3/8 x2 in this case.
Oh, what happened to gamma?
So in this case, gamma is equal to 1, and so I'm giving you we're working with our specific example. Yeah, and so gamma would be sitting out here, but since we're just assuming that's 1. Next, we're going to apply it at I is equal to 3. Okay. Next, we're going to apply it at I is equal to 4. Right, and then finally, when we apply it at I is equal to 5, we get the final equation for that. Okay. All right. Any questions on this so far? Okay. And so, at first glance, you would think that we're done, right? And so we applied finite differences to the equation. We got 5 equations, right? And each of these is a valid equation. And so we can solve for our 5 unknowns, right? And so our 5 unknowns in this case would be the phi values at each of the grid points here. And so it would be like phi 1, phi 2, P3, P4, P5, right? Right, so we have 5 phi values, we have 5 equations, we're Gucci, right? So we're good to go. Unfortunately, that's not the case because we have a couple unwanted guests, right? Right, we have phi 0 and we have phi 6, right? We don't have a node 0 and we don't have a node 6. Okay. Right, and so since we don't have those those nodes, we can't really use those equations because we have nothing that we can really plug into those. And so that kind of actually invalidates the first equation and the last one, right? Right. And so since we don't have the appropriate number of neighbors to use the finite differences, we have to come up with something different for the first and last nodes of the domain. Okay? All right, question. So can we set them equal to something else? Yeah, we'll get there in a second. Yeah. Okay. All right. So let's look at where nodes 1 and 5 are, right? So you can see that node 1 here is on the very left edge of the domain. And node 5 here is on the very right edge of the domain, right? What do we have that's conveniently at those parts of the domain? We have our boundary conditions, right? And so, instead of using a finite difference, equation for the endpoints of the domain, we can instead take our boundary conditions and turn them into, the appropriate equations. Okay? Okay. All right. And so, there's 2 different ways that we can do this, and that depends on, what type of boundary conditions that we're looking at. And so let's look at the Dirichlet boundary condition first. And so, we're basically going to take our boundary conditions and turn them into, into the appropriate type of equation that we're going to use. Okay. And so Dirichlet boundary conditions are very simple. And so Dirichlet boundary conditions, we're making a direct specification of the solution, right? Right. Let me make this more general. Right. So remember, the general form for a Dirichlet boundary conditions is we say that when x is equal to the Dirichlet boundary, okay, which in this case is x equal to 0. But you can have Dirichlet boundaries on either side, and so you can have a Dirichlet boundary on the other side of the domain as well. Okay, that means that we're just going to directly specify the solution variable. Okay? And so in this problem, we have a Dirichlet boundary condition at x equal to 0, right? And in fact, what we have is phi at x equal to 0 is equal to 1. Okay. Okay. Another way that we can represent this is, what's the grid point at x equal to 0? The grid point at x equals 0 is just phi 1, right? And so another way that we can express this boundary condition is to say that phi1 is very simply phi1 has to equal 1. Right? Right? And so this equation is simply the one that we're going to replace the I is equal to 1 equation with. Okay. Right. So Dirichlet boundary condition is very simple, right? And so we basically, instead of this whole equation right here, what we can say instead is phi1 is equal to 1. Okay. Right. And so that replaces the I is equal to 1 equation, right? Because remember, we can't use the I is equal to 1 because equation because we don't have phi0. Okay. And so we kind of get rid of that entire equation, and then we replace it with the boundary condition, which is, phi1 is equal to 1. All right, any questions on that? Okay. Okay, and so the other type of boundary condition that we have is a Neumann boundary condition. And so Neumann boundary condition, remember, is a specification of the derivative. Okay, and so in this case, we have d phi dx is equal to gamma, which is the most generic form, okay, of the Neumann boundary. But in this case, we have a Neumann boundary condition at x is equal to 1. Okay. Right, and so we have d phi dx at x is equal to 1. In this case, is equal to 0. Okay. Right. And what do we have here, right? So what we have here is a derivative. And so for a derivative, we can just replace that with a finite difference. Okay. Let's try central difference first. Okay. Remember, this is a first order derivative. Okay. And remember, this is when I is equal to 5. Right, and so if I is equal to 5, remember our central difference scheme is I plus 1 minus phi I minus 1 divided by 2 delta x is equal to that, right? Okay. Right, and so this is a finite difference, representation of that derivative. Okay. So you have phi 6 minus phi 4 divided by 2 delta x, right? And since our Neumann boundary condition in this case is 0, then we say that this quantity there is equal to 0. Okay. But wait a minute, you're probably saying, this is the exact same problem that we had before, right? And so we have phi 6 here, and so we can't have phi 6, right? Because remember, node number 6 doesn't exist because our domain only goes up to node 5, right? And so we actually can't use a central difference scheme for this, right? Because then that runs us into the same problem. And so we need to use one of the lower order schemes here, okay? And so among our lower order schemes, we have backward difference and we have forward difference. Let's try backward difference. Okay. Remember, backward difference, the way it's defined is phi I minus 1 divided by delta x. Okay. Okay. So let's go ahead and plug that in. And so we have, we apply it at I is equal to 5. What we get is phi 5 minus phi 4 all divided by delta x. For delta x, I'm just going to plug in is 1 over 4 is equal to 0. Okay. We can multiply 1/4 on both sides just to just to get rid of that. Okay. And we have 1/4 times 0, which is just 0. And so in the end, we get phi5 minus phi4 is equal to 0. Okay. And so this is a valid equation that we can use because all the phi values that we have here are actually valid members of our domain. Okay. And so let me put a note here just to just to kind of make things helpful, because we kind of did a lot of steps for this. And so for Neumann boundary conditions, but you have to use either a forward difference or a backward difference, depending on which one gives you a valid neighbor. Okay. I don't think we're gonna have enough time for the punchline, which is too bad. But I'll save the punchline for next time. Okay. And so now that we have this Neumann boundary condition, we can go back to our system of equations and replace that last equation with this one. Okay. So let me go back up. I know maybe not everyone's finished writing that down, so let me come back up here. Oops. So this is 5, phi5 minus phi4 is equal to 0. Okay. Okay. And so now once we've done that, now we have our 5 equations and our 5 unknowns, right? No more unwanted guess. And so it's purely just all phi 1 through 5. Okay. And so the next step in this problem is you would basically put this into matrix form and then solve that in MATLAB. Okay. Okay. And so I don't want to keep you guys because I know it's 6:45, but so are there any final questions on this before we wrap it up for today?
Yeah, so we don't necessarily need all of the boundary conditions to solve the problem, just the specific ones at the edges.
Right. So you're going to be given 2 boundary conditions on these kinds of problems. So you're going to end up using both of them, because you need one on one end and one on the other end.
Okay.
Yeah.
Okay, thank you.
Yeah. All right, question, Samson. Oh yeah, I can pull the page down. Yeah, so you can use the same equation as long as it has the same terms as our domain just has equation. Yes. Yeah, and so the reason we use the boundary conditions is so that we get everything in terms of the nodes that we actually have in our domain. That's correct. Okay. All right. So thank you guys for coming today. On Wednesday we'll actually pick up kind of right where we left off here, and we'll actually talk about how to implement this in MATLAB. So Wednesday will be our first day where we actually do something in MATLAB. Okay. All right. So thank you guys for coming today. Hope you guys enjoyed the lecture. I hope you guys enjoy the rest of your evening, and I will see you on Wednesday. Thanks, guys.
Thanks again, Dr. Chang.
Just mentioned.
Yeah.
This is the current row, and then here choose the 1, 2, 5.
Yeah.
Why have
Right. So as this loop iterates, the concept of the loop is that it's going to repeat itself, many times, right?
Yeah.
And each time that it repeats, the I variable is going to increase. So the first iteration of the loop, I is going to equal to 1. The second iteration of the loop, I is going to go up to 2, and this is going to continue up until it goes up to 5. And so you can make an if statement based on what the value of I is. And so, you can think of, the first time that it iterates, I is going to equal to 1. And so if you say if I is equal to 1, that means you're in the first row. Right?
So it's like, so for example, I is in the first row is here.
Exactly. Yeah.
And when I say I equal to 1,
I equal to 1. So you're doing a check.
I equal to 1. So it means the remainder is 0.
So we're not doing any remainders in this case. So we're just
Yeah.
we're just checking the value straight up.
So if so just put the -2 here, right?
So the -2 is something that happens on every row. And so remember we talked about at the end,
It
that's
is happening everywhere.
right. So that's something that you put at the end. Right. So outside the if statement, remember I have that one line of code. And so the fact that -2 is occurring every row, that's where you would put it right after the if statement because it occurs first row, second row, third row, fourth row. It occurs every single row. And so
Oh, so you mean so the -2 is in the first row is in the first place, and the second row is in the second.
exactly,
place,
yes.
and the third row in the third, and the fourth one is also like the same. So just
Right. So the thing that's different in each row is the number of ones that are there and where you actually put it. And so for the first row, you can see we only put a 1 to the right of the diagonal. Right? For rows 2, 3, and 4, we put a 1 on the left and the right of the diagonal.
Yeah.
And then for the last row, we only put a 1 on the left. And so those are your three cases, and that's how that's what you would put inside the if statement.
Okay, I see.
Yeah.
Thank you.
Yeah. Yeah. What's up?
Did you want us to send like a file like this, like in PDF? Do you want the actual map? file?
The PDF is good. So I'm just going to kind of read the code just real quick.
Okay.
And the PDF helps me because then I can open it up in Canvas, and so I don't have to open it back. It makes it easier to print this.
All right, thank you.
Yeah. Yeah.
Where did this mention? Was it just like the coding you're supposed to submit?
I mean, there's a couple other, there's like some conceptual questions at the
Yeah.
beginning, right? Yeah, so answer the conceptual questions and then the code as well.
Okay, just the coding.
Yeah. So if you can put it all in one document, the code, that would be most helpful. And I can just scroll down and just read it.
Okay,
Yeah.
that's good. Thank you.
Yeah. Oh, wait, what? Oh, no problem. I mean, people kind of come and go all the time. So it just kind of drew my attention for a bit, but you weren't disruptive at all. So yeah, don't worry about it.